Whenever you're asking a question of the form, what is X, especially when X is something that everyone already basically understands, I think it's good to be clear about what you're looking for, because there's never going to be an answer to that question that's completely satisfactory, and so you don't want to be too picky. I think sometimes people get very excited about the fact that we know how something works, but we don't really understand, like, what it is, man. And yeah, sure, that's one way of looking at it, but you can say that about pretty much anything, so it's not really that interesting of a statement. For example, you sometimes hear things along the lines of only 5% of the universe is ordinary matter, the other 95% is dark matter and dark energy, and scientists don't understand what those are. But dark energy is explained pretty well by just adding one cosmological constant term to Einstein's field equations of general relativity. Of course, we don't know why that term is there, or why the cosmological constant has the value that it does, and we suspect it's only an approximation to some deeper theory. But you could say the exact same things about, for example, electrons. Why are there electron terms in the standard model of particle physics? Why does the coupling constant that gives electrons mass have the particular value that it does? We suspect that's only an approximation to some deeper theory too, so I think it's misleading to say that we understand ordinary matter and we don't understand dark energy. Depending on the level of understanding that you're looking for, we either understand both or we understand neither. So when it comes to distance, I want to try and explain the level of understanding that I'm looking for. See, the act of defining the distance from A to B implicitly assumes that there is such a way to define a thing consistently, so that you always get the same answer. And that's not a logical necessity. It relies on assumptions about the world that are based on empirical observations. Assumptions that, in fact, turn out to be false, as shown by special and general relativity. A good definition of distance should make it clear what these assumptions are, stated in terms of things that are more fundamental than distance, so that we're able to actually think critically about the utility of the term. It's not that distance is a useless idea. Far from it, no pun intended. But it turns out to only be coherent in certain contexts, and these contexts are exactly the contexts in which those assumptions are valid. To see what I mean, we'll start by looking at time instead. I guess because time is even more confusing than distance, it seems like more work has been done on being careful about definitions, or at least the work that has been done has been easier for me to find. I've got From Eternity to Here by Sean Carroll from the library here, and there's a lot of cool stuff in here about the arrow of time and entropy and cosmology and stuff, but for our purposes all we really need is this one sentence in the first chapter. As a matter of empirical fact, rather than logical necessity, there are some objects in the universe that are consistently periodic. They do the same thing over and over again, and when we put them next to each other, we find them repeating in predictable patterns. Next to one another is the key phrase here. We're trying to define time, so we can't use time. We can't talk about some object being absolutely consistent in the sense that the same amount of time passes every cycle. We can only talk about relative consistency. Every time object A repeats X cycles, object B repeats Y cycles. There are lots of examples of periodic objects that all appear to be relatively consistent with one another, and so we arbitrarily selected one of them and defined times in terms of it. I mean, not arbitrarily, I'm sure there were practical reasons that went into picking the electromagnetic radiation emitted by a particular transition of the cesium-133 atom, but fundamentally it doesn't really matter which one you pick. Now you should be a little suspicious that what I said was circular. A and B are relatively consistent if every time A repeats X cycles, B repeats Y cycles. There clearly is something temporal about this definition. But what we're trying to define is the time between two events as a numerical quantity, and we're not using that anywhere. To rephrase, say we simultaneously observe A and B in their initial states. Since observation relies on light and we know light travels at a finite speed, we should also specify that A and B are next to each other if we want to be sure that they're really simultaneous. Then we keep observing them and note each time we observe each object return to its initial state. Whenever we observe A return to its initial state for the x times nth time for some integer n, we will simultaneously observe B return to its initial state for the y times nth time, if A and B are next to each other. So if we see A finish its second cycle at the same time B finishes its third cycle, we better see A finish its fourth cycle at the same time B finishes its sixth cycle. The only temporal idea we're relying on here is the idea that our subjective experiences are uniquely ordered. Each one is either before, after, or essentially simultaneous with every other one. One could hypothetically explain this by saying that each one happens at a particular numerical time, 2 p.m. Tuesday, 5 p.m. Wednesday, and numbers are ordered, so therefore experiences are ordered. But the explanation, I think, is better in reverse. We directly observe that experiences are ordered, and we know that numbers are ordered, therefore we can use numbers to label the moments that we experience. By itself, though, that doesn't guarantee that the numerical difference between moments has any consistent meaning. That only happens if we calibrate the numbers against one of these periodic objects that is relatively consistent with other periodic objects. In other words, use a clock. This is all summed up in the wonderfully concise phrase, "Time is what clocks measure." Even though this sort of sounds like a non-answer, I think it's really a great definition because it makes it very clear that the existence of time as we know it depends on the existence of clocks. If it turned out that what we thought of as clocks were not, in fact, relatively consistent with each other under all circumstances, we would know that the time elapsed would only have meaning when restricted to the circumstances under which they are relatively consistent with each other. And wouldn't that be interesting? So the natural equivalent of this would be distance is what rulers measure. As long as we can figure out what we mean by rulers, this is also a great definition, because it makes it very clear that the existence of distance as we know it depends on the existence of rulers. So what is a ruler? Intuitively, it's a straight line that is rigid. In other words, if you don't break it, it always remains straight, and the distance between any pair of points on it doesn't change. But of course, we can't use the word distance here. Instead, just as we got around using the word time by saying a clock is something that is temporally consistent with other clocks, we can get around the word distance by saying that a ruler is something that is spatially consistent with other rulers. And just as we invoked the temporal order of our experiences to define temporal consistency, we'll need to invoke some sort of spatial order to define spatial consistency. I think it's fair to say that the spatial order of points along a straight line exists and is clear, without getting too much into the philosophical weeds. But at the very least, the spatial order of the points is definitely more fundamental than the distance between the points, and so that's good enough for now. The good news about rulers is that we can consider every point on them to be marked, and so we aren't limited to the endpoints like we are in the case of a periodic object returning to its initial condition. So spatial consistency goes like this. Say we have two rulers, A and B. A1 and A2 are points on A, B1 and B2 are points on B, and say we simultaneously observe A1 touching B1 and A2 touching B2. Then, whenever we simultaneously observe A1 touching B1 and A2 in the same direction as B2, it must be the case that we also simultaneously observe A2 touching B2. If we have two rulers and the 0-inch marks are touching, but the 6-inch mark is touching the 8-inch mark, something's gone wrong. The bad news about rulers is that it's not immediately clear what we mean by a straight line. A straight line is often defined as the path between 2 points with the shortest distance, but that's not going to work for obvious reasons. We could say that basically I know it when I see it. A straight line is something that looks straight when viewed from every angle, but I don't really like this. It feels vulnerable to optical illusions and refraction and stuff. We could define it as the path an object follows in the absence of any net force, but practically, how do we know if something has no net force on it? Because it's moving in a straight line. So that seems hard to use. Again, I think relying on relative consistency is our best bet here. So I'll propose the following definition. Empirically, there are lots of basically one-dimensional objects out there where, for any two of them, if they are touching at 2 points, they are also touching at all the points in between. We call these straight lines. So rulers are just objects that are basically one-dimensional that fit this criterion and also the earlier one. Notice that this definition calls the very existence of straight lines into question, and I think that's unavoidable because when you get into general relativity, nothing really behaves like a straight line anymore. A couple things to note. Our definition of distance relied on things happening at the same time. We have to observe the two parts of the rulers touching at the same moment, or we learn nothing. And our definition of time relied on things happening in the same place. The clocks have to start and end next to each other or we learn nothing. Normally we think of space and time as completely independent things, and one of the counterintuitive parts of relativity is coming to terms with the fact that they really should be thought of as different aspects of the same thing, space-time. But already from careful consideration we can see that they're not as logically independent as we might have thought. So do clocks and rulers, as defined here, really exist? The punchline, of course, is no. The assumption that my clock and your clock are relatively consistent no matter what is not true. It doesn't matter how good the clocks are. Nowadays, we believe in this assumption only if, strictly speaking, the clocks remain next to each other the entire time. So time, therefore, is only well defined relative to a specific path that a clock might take. The assumption that my ruler and your ruler are relatively consistent no matter what is also not true. Again, it doesn't matter how good the rulers are. Nowadays, we believe in this assumption only if, strictly speaking, the rulers are at rest relative to each other during both measurements. If they're not, then an observer at rest with respect to ruler A and an observer at rest with respect to ruler B will make the same sets of observations, but they will disagree about which ones are simultaneous. And we have no direct way of verifying that two events happened at the same time, only that they were observed at the same time. So we're forced to admit that both observers are equally correct, and that absolute simultaneity is not a meaningful concept. Length, therefore, is only well defined relative to a specific path that an observer holding a ruler might take. These results are certainly surprising, and Einstein is certainly a smart guy for figuring them out, but I hope this demystifies them a little bit. There's absolutely nothing paradoxical about getting rid of absolute distance and time. The truth is that they were never built on that solid of a foundation to begin with. Don't get me wrong, I still catch myself thinking things like, okay, but what really is the distance between A and B? But this is sort of like asking, okay, but who really is the mother? It's nonsensical. Everyone's got their own mother, except for siblings, and everyone's got their own equally valid idea of distance, except for observers that always remain next to each other. I think there's a good general lesson here. Definitions are great. We can't do science without them. But the good scientist, like the good Buddhist, does not get too attached to any particular idea. Whenever we define something, it's because that thing appears to be in some way consistent. Over time, we get used to the idea, and we start to take that consistency for granted. But almost always, it's built on nothing more than repeated empirical observation. Every time X happens, Y happens. It's of the exact same form as arguing all swans are white based on repeated observations of white swans. This is all well and good as a working hypothesis, as long as we're open-minded enough to recognize the black swan when we see it.